Hello everyone, my name is Manish. My team members are Dhruv, Rushali and Priyanshi. We are going to teach you machine unlearning. In this world where we are engaged in making AI learn things, can anyone think of making them forget things? Let me get it to you. What if you could teach an AI to forget something completely like it never taught it, without starting over from scratch? Sounds like science fiction, right? But it's real, and it's called machine unlearning. Today, in our Teach Me Something section, we are going to take you into this fascinating world. Imagine a social media app with millions of user photos powering its AI. One user says, "Delete my data now." How do you make that AI forget that photos without breaking everything else? That's the puzzle machine learning solves. And trust me, it's cool as summer. Let's dive in. What exactly is machine learning and how does it matter? First, let's set the scene. You all know machine learning, training AI to spot patterns, like recognizing cats in photos or predicting stock prices. We feed it data, tons of it, and the model learns by tweaking its internal settings, like adjusting a recipe until the cake's perfect. But here's the catch. Once that data is baked into the model, it's stuck. There's no easy undo button. If a user says, "I don't want my photo in your AI anymore," or if a company finds out some data was biased or even illegal, what do you do? You can't just pull one ingredient out of a baked cake. Or can you? That's where machine learning comes in. The classic definition of machine learning is machine learning can be broadly described as removing the influences of training data from a trained model. At its core, unlearning on a target model seeks to produce an unlearned model that is equivalent to, or at least behaves like, a retrained model that is trained on the same data of the target model minus the information to be unlearned. Now, why is it important? Imagine a world where your data is double edged, sword powerful, where when used right, but risky when it lingers too long. Today, I want to walk you through why users might demand their data be erased from a system. It boils down to four big reasons: security, privacy, usability, and fidelity. Let's dive in. First, security. Picture this: a deep learning model humming along, helping doctors diagnose patients. Suddenly, an attacker slips in adversarial data, fake inputs, so sneaky even humans can't spot the difference. The model stumbles, spitting out wrong predictions. In healthcare, that could mean a misdiagnosis, a wrong treatment, or worse. To fight back, the system needs to detect this poison and wipe it out fast with something called machine learning. It's not just about protection, it's about survival. Next, privacy. Laws like GDPR in Europe or California's Consumer Privacy Act aren't just legal jargon, they are shields of users, giving them the right to be forgotten. Why? Because leaks happen. Cloud systems juggling backups and copies can accidentally spill your info. Or take genetic data. Machine learning can accidentally expose someone's DNA markers. Users aren't paranoid, they just want control when the stakes are that high. Then there's usability. Ever search for something odd by mistake, like an illegal product, and suddenly your phone won't stop suggesting it, even after you have scrubbed your history? That's a system failing to forget. It clings to noise or outdated data, serving up recommendations that annoy rather than helping them out. When an app can't let go, users walk away. Finally, fidelity or fairness. Machine learning isn't perfect. It can inherit biases from messy data. For instance, AI beauty contests favoring highlighted skin tones. The culprit? Training data skewed toward one group, like ImageNet's mostly white faces, or models accidentally latching onto things like gender or race in job applications. Unlearning those flawed bits isn't optional. It's how we make AI less unfair. So, whether it's dodging attacks, guarding secrets, improving experiences, or fighting bias, users have real reasons to say, "delete my data." And in a world where trust is everything, systems that can't forget might just find themselves forgotten. Now let's explore the types of machine learning.
Okay, now let's talk about types of machine learning. Let's talk about a fundamental concept in responsible AI development, machine learning. Specifically, the two major approaches that dominate the field today, exact unlearning and approximate unlearning. At its core, machine unlearning is about enabling a model to forget specific data points it was trained on. This becomes especially important when dealing with legal rights, like the GDPR's right to be forgotten, or when users revoke consent. In such cases, it's not enough just to delete data from the storage. We also need to make sure the model no longer reflects anything it learned from the data. But how do we actually do that? That's where the distinction between exact and approximate unlearning comes in. Now let's start with exact unlearning. This is the most rigorous approach. It ensures that after the unlearning process, the model behaves exactly as if the target data point had never been used in training at all. In other words, the final model should be statistically indistinguishable from one trained from scratch on the remaining data. The simple way to achieve exact unlearning is quite literally to retrain the model from scratch without the data you want to forget. Technically, it works, but practically, especially for large models or frequent deletion requests, it's often too slow and resource insensitive to be feasible. To address this, some techniques like SISA aims to reduce retraining costs by breaking the training process into manageable chunks. So instead of retraining the whole model, you retrain just a small part of it. The part that was exposed to the data point you want to unlearn. While this helps improve efficiency, it's still a form of retraining and the costs can add up. Now, in contrast with this, we have approximate unlearning. Instead of retraining the model completely, approximate unlearning tries to efficiently estimate what the model would have looked like without the target data. It aims to reduce or reverse the impact of the data through clever updates, like fine-tuning the model on the remaining data or use mathematical tools such as influence functions to estimate how the data point affected the model's weight. This approach is significantly faster and more scalable, making it attractive for real-time or large-scale systems. However, the trade-off is that it doesn't guarantee complete removal of data's influence. Some traces might still linger, so while the model might behave similarly to that one that never saw the data, it isn't a perfect match. This introduces uncertainty which can be problematic, especially in legal or high risk settings where full compliance is required. To summarize their key difference in plain terms, exact unlearning is about certainty. It gives us a guarantee that the model has truly forgotten, but at a high computational cost. Approximate unlearning, on the other hand, is about efficiency. It gives us a quicker solution, but with weaker guarantees. Which one to use depends on the situation. If you're building a medical model or something with legal exposure, exact unlearning might be safer choice. But if you're running a recommendation system with millions of users and daily updates, approximate unlearning might be your only practical option. Researchers are now trying to bridge this gap to make exact unlearning more efficient and approximate unlearning more trustworthy. New methods are being explored that embed unlearning capability into the training process itself or combine modular training with formal guarantees. Ultimately, as the AI continues to evolve, unlearning isn't just a technical challenge. It's a matter of trust, accountability, and user control. The real goal is to design models that can learn, adapt, and forget responsibly.
Before we get into the techniques, let's start with the simplest way to unlearn, something called as naive unlearning. Let's talk about naive unlearning first. It is the most obvious way to forget the data. Picture this. You have got a model trained on 100 photos, including the photo ID file. A user say, remove photo ID file. With the naive unlearning, you take your full dataset and kick out the photo ID file. So now you have 99 photos and retrain the entire model from the scratch. Start with the random weights, run all the training steps, forward pass, backward propagation, and that works. Okay, on the 99 photos. Then the new model act like photo ID 5, never there. It is exact. No trace of that photo left. Sounds good, right? Well, not quite. Here is the problem. It is slow, really slow. If your dataset is huge, say a millions of photos, or your model is complex, like a deep neural net, retrain the could take hours, days, even weeks. So it's like rebuilding a house just because one brick's cracked. SISA, said isolated, sliced, aggregated technique. It is a game changer in a machine learning, especially when we need to forget the data. Imagine you are a tech company, say a social media giant. You have trained an AI on a million of user photos. One day a user say, delete my photo from your system. Now, retraining that massive model from the scratch could take a days, even weeks. That's where SISA comes in. It is a fast, smart, and it's all about making AI to forget efficiently. Step 1, Sharding. Split the data. We start by taking our dataset, say 100 of photos of cat, dogs, anything, and split into smaller non-overlapping parts called the set. If we take 5 sets, each one gets 20 photos. Think of it like tearing a big recipe book into the 5 smaller cookbooks. Why do this? Because if we ever need to remove one specific photo, like photo ID 5, it only live in a one set. That's way we influence it is neatly contained right from the beginning. Step 2. Isolated. Training submodels. For each set, we train a separate mini model. So with 5 sets, we train 5 models. Call them M1 through M5. Each model only seen its own set data. No sharing, no overlap. It's like giving each student their own textbook chapter to study. If photo ID 5 is in set 1, only model M1 train on it. The other model M2 to M5, no. They never ever shown it exists. This is the isolation is a key. It limits where the photo ID files impact shown up. Step 3, slicing. Breaking it down further. Now comes an optional but a smarter step, slicing. Inside each set, we can break the data down further. Let's say set 1 has 20 photos. We divide it into 4 slices, 5 photos of each. When we train M1, we go slice by slice. Train on slice 1, save the checkpoint. Train slice 2, checkpoint again, and so on. It's like reading a chapter in a small chunk and saving your place. Why do this? If photo ID 5 is in slice 2, we can restart from the checkpoint just before slice 2 and skip it. No need to retrain from the scratch. It speed up unlearning through it does add some more setup. Next step is aggregated, putting it together. Now let's put it together with the aggregations. We got 5 submodels. How do we make a final prediction? Simple, they vote. Say we show them a new photo. M1 say it is a cat, M2 say it is a cat, M3 say it is a dog, M4 say it is a cat, M5 say it is a cat, majority say cat. So the final answer is cat. But for numeric output, like a predicting a price, we just average their result. It's like getting input from the jury. Everyone weigh in and we get a well-round final decisions. Now, unlearning with SISA. Alright, here's where all those steps come together. Unlearning in action. Let's say we need to delete photo ID 5. We already know where which side it belong to. Side 1. So we just focus on its model M1 and the rest of the model totally untouched. If we train M1 without slicing, we simply retrain it from the scratch, leaving photo ID 5. But if we use the slicing and that photo say in a slice 2, we can rewind to the checkpoint just before slice 2 and continue the training without it. Once M1 is updated, we plug it back into our aggregation step. That's it. We got a new final model M dash and photo ID 5 is effective gone. No need to retrain everything. No need to touch unrelated data. That's the beauty of SISA. Fast, clean, precise unlearning. So let's see the demo of SISA. So first we import the necessary libraries and this is the dataset that we are using. So let's first load the dataset. After loading the dataset, we converted the images into their feature vectors. So for that we are using the ResNet 80. After that, the way we train the model in a machine learning, the same way we train the logistic regression model. And this is the baseline model. Its accuracy is 95%. So let's see the demo of Naive Unlearning. So as we discussed, we just remove the photo ID 4 and retrain the entire model from the scratch and save it. So our dataset is very small and it is an easy task. So as we can see, the accuracy is not affected. So let's see the demo of SISA. So as we discussed, we first divide the data set into the number of set. So here the number of set is 5 and the data set is divided into the set, and for each set data set is further divided into the each slice, and we train the model on the each slice and we save it into the checkpoints and we get the submodels. After that we do the aggregation step as we discussed for the final output. Let's do the unlearning with the SISA. So first we find in which set the image belong to. After that we just remove that image from that set, and for that set we again train the models on the each slice and update in the final model, and this way we can do the unlearning by using the SISA.
So let's talk about the challenges and machine unlearning. So first one is the spectrum of unlearning hardness. Second one is the copyright protection. Third one is the retrieval based AI system. Fourth one is the AI safety. So let's talk about the spectrum of unlearning hardness. Example seen later in a training should be easier to unlearn because they only slightly shift the model's weight, allowing us to revert the gradient or restore the checkpoints. However, they are harder to remove over a time since earlier examples are gradually forgotten and newer examples become more persistent. This creates the paradox between the memorization, forgetting, and the unlearning. If model forgot early data, later data becomes harder to unlearn. The model's knowledge structure play a key role in determining which data is easier or harder to remove, making this challenge yet to be fully understood. So let's talk about the copyright protection. Unlearning is often seen as a way to address copyright concern in AI models. If a model memorizes copyrighted content, we might be able to erase it, but current unlearning methods lack strong guarantees and the legal framework remain unclear. In practice, the fair use doctrine allows limited use of copyrighted content under certain conditions. So, unlearning might not always be needed. OpenAI, for example, has focused on a prompt control, content moderation, and alignment tools to reduce the risk of regularities copyrighted materials. There are also economic solutions like retraining services or indemnifying users as with OpenAI's copyrighted shield. While unlearning seems promising, it needs legally enforceable mechanism to become a viable solution. So now talk about the retrieval-based AI systems. Instead of making a model forget, we can store sensitive content externally, which is allow the model to retrieve it when necessary. If deletion is requested, we can simply remove the data from the external database. This retrieval-based approach has shown promise, but it's not without challenges. Removing copyrighted content is not easy. Paraphrase or summarize can be difficult to detect. Additionally, some model behavior like writing style or a preferences can't be retrieved from a database. Feeding protected content during the inference also open up the security risk. Moreover, while retrieval-based systems are useful, they can't fully replace the power of the training. Relying on it too much on external data might limit the model's overall effectiveness. So let's talk about the AI safety. As AI safety advances, unlearning is being explored as a safety tool. The challenge lies in determining what to unlearn, whether it's a dangerous knowledge, harmful behavior, or a risky capabilities. Identifying and remove these elements is far from straightforward. Model poisons and backdoors are difficult to detect and even harder to unlearn. Similarly, unlearning manipulative behavior or bias, which are deeply embedded in the model, is challenging. The hardest task is unlearning abstract tendencies like power seeking behavior, which are not linked to specific knowledge. Even if we target the right path to unlearn, the process is costly, time consuming, and can impact the performance.
In conclusion, machine unlearning possesses a range of challenges that extend across technical, legal, and ethical domains. While it holds promise as a tool for responsible AI deployment, the complexities of implementing effective unlearning, coupled with uncertain legal frameworks and the ethical implications of such a process, make it an area requiring continued research. As AI systems evolve, it is essential to integrate unlearning capabilities from the outset, ensuring that models are designed to adapt and comply with privacy, safety, and copyright considerations from the start, rather than trying to retrofit unlearning later on. This proactive approach will be the key of addressing the multi-faced concerns surrounding AI's future user impact. These are some of the references that we've used. Thank you.